Hello, so today we are going to talk about this problem, rearranging fruits from contest 331. So the problem says we get two fruit baskets that each contain n fruits, right? And we get, these baskets are basket 1 and basket 2. And they represent the cost of fruits in each basket, right? So basically each value is the cost of the fruit. And you want to make the two baskets equal. That's our goal. And the operation we can do for that is picking two indices, I and j, from each basket and then swapping them, right? And the cost of the swap is going to be the min of the value for each index, I and j, right? And so they say here we want to make the baskets equal, and by equal they means not necessarily exactly the same values in the same places, but just that if you sort them, you will get the same basket, right? So basically, it means that each number should occur the same number of times, right? And the goal of the problem is to minimize the cost to make both baskets equal. And if we can't, we want to return -1. Right? So for example, if there is a value that, let's say 5, that is here, but is not in basket 2, then we can't make them equal. So we want to return -1 in that case. Okay, so that's the problem description. Now, if we take a look, for example, at this here, we can swap one of basket 1. So we can swap this one with this one, and we will make them equal that way, because then we'll end up with this one and this one. And you can see 2 occurs twice in both. 1 occurs once, and 4 occurs once. So they are equal. Once we sort them, they will be equal. For the second example, 5 is here, but is not in the first one. The same thing with 4. And so we can't make them equal, no matter what swap we do. Yeah, so that's the problem. Now let's see how we can find a way to solve it. So first, let's just remember a couple of observations that we said initially. The first one is that basically if a number is in one basket but not in the other, then we know we need to return -1, right? Because it's not possible to make them equal. If you have, let's say, 5 in basket 1 but you don't have it in basket 2, then no matter how many swaps you do, you'll just end up putting this 5 in the other basket, and they won't be equal, right? So that's the first observation here. The second thing is, let's generalize this a little bit. Actually, it's just not one in the other, right? Because let's say you have 3 2s in basket 1 and you have 2 2s in basket 2, right? And maybe you have other values we don't care about. Then with these two already we can make them match. That's fine. So we don't need to do anything. But for this one, no matter what you do, even if you swap it and remove it from here and put it here, you will just end up with the same problem as a number that doesn't exist in the other one, because you can't just bring a new 2 to match it with it, right? So you will always have a problem with this 2. It will always prevent you from making the two baskets equal. And what's unique here is that, but in the other hand, actually, if you have 4 2s, let's say, in basket 2, and with some other values, and only 2 2s in basket 2, then now you can make it work, possibly depending on the other values, because these two match already, that's fine, right? But for this, you could pick one of these, swap it, and now you have 3 2s on each side, and maybe you have here some other values. You have 3 2s on each side, and now this one matches with this one, and you can just look at the other values, right? And so what's the distinction here if we generalize this? This actually applies to all the odd values. So all the odd values, it's not going to be possible if you have an odd count in one basket. Now, if you have an even count, you should be able, at least for these values, you should be able to make it equal, right? So the observation here is that so the observation that we can make here is that if the count in in basket 1 or 2 of one number is odd, then we can immediately return -1. Okay. And we can even, like, to do this in a really easy way, instead of doing the count for each one, we can actually just collect the count together for all of them, right? So basically just do the count of B1, the count of occurrences of B1 plus the count of occurrences of B2. And let's say this is the overall count. In this count here, just check if the count is for one value is odd, then we want to return -1, right? And the only way for this count to be odd is if one basket has an odd count, right? And so that will work, but instead of doing it for each one of them separately, we can do it once, okay? So those are the two observations. The other observation is that is a little bit more tricky, which is, okay, actually let's do another first one. So now with these two, the other thing is that the goal here is to minimize the cost to make the baskets equal. And the cost for each swap, right, is the min of the value from B1 that we want to swap, so B1I and B2J. So what this tells us basically is, to be able to get the min, we can just pick the smallest value from one basket and the biggest value from the other basket. That way, basically, we will get each time the min cost, right? So, yeah, because if you can think of it as picking the min value from one basket to kill the biggest value, so you can get rid of it and not have it in the cost, right? And so, so basically what we want to do is take the smallest value each time and just swap. So what that would mean here is with the sorted B1, by the way, we are going to keep only what's not matched anymore. We will do a processing step to keep only those that don't match. What do I mean by that? So for example, in the initial example that we had, B1 was like this, B2 was like this, 1, 4, 1, 2. These match, okay? And these match already. So for these that don't match, we don't need to do any additional processing. We only need to check about these and try to swap them, right? And so suppose that we did that processing already and we have some B1 with, let's say here we have, let's call it A1, A2, some other values, and that are sorted, of course. So this is sorted in increasing order. And let's say we have this one, B1, B2, B3, that are also sorted in decreasing order, right? In increasing order, right? Then what we want to do is basically just group the smallest value with the biggest value, right? Because if you don't, and let's say you group it with this one, then you will get a higher value. But if you group it with this one, then this one may be bigger than AN, smaller than AN, and you will incur a higher cost than A1. So it's always better for you in a greedy way to take the smallest value from one of them, pair it with the largest value from the other one. Basically, in that way, the cost is the smallest one. Basically, killing this one for you, killing the cost of this one and removing it so that you don't incur that cost. So that's the idea. Now, the other thing is that what if you had a value for the smallest value of all? Let's say the smallest value of both baskets. Let's say we have one maybe in here. Maybe B2 was equal to B1 was equal to 1, for example, right? Then no matter the swap you do, there is another swap that is potentially smaller, and that swap is basically swapping A1 with 1. So let's say for A3, you could always swap 1 with A3, right? And then swap back A3 with that one, right? So let's say you have this one here. What I mean by that is you could first swap A3 with that one. So now you have one here and you have A3 here, right? And then you wanna, for the value that you wanted to swap it with initially, let's say it's B3, you can swap again 1 with B3, right? So you'd get 1 here and you would get B3 here. And you can see what we ended up with. We still got A3 swapped with B3, but we did it just by using two swaps that involve this value 1 because it's the min for each of them. Let's say 1 is smaller than A3 and 1 is smaller than B3. So what we did for the first swap, we swapped 1 with A3, so the min cost is 1. And then in the swap 2, we swapped 1 with B3, so the cost is 1 because that's the min, so overall cost is 2. So potentially this 2 may be smaller than if we just did swap A3 with B3. And in this case, if we have this here, then it is, let's say if both A3 and B3 were smaller than 2, then were bigger than 2, then this is better, right? So if A3 was bigger than 2 and B3 were bigger than 2, then it's better to do the swap this way than to do it just by swapping A3 and B3, right? And so that's just something to take care of and pay attention to. So in that case, we just need to do a special case where we say we have a min cost, which is going to possibly be a solution for all other swaps, which is just the minimum of both, right, of all of the values in B1 and B2, and so the remaining values, of course. And so let's just have our overall counter get the keys. Remember, the overall counter has all the keys in the 2 baskets, right? And we removed but basically all of the keys in the 2 baskets, and we take the min multiplied by 2. Because we do the swap 2 times here, like 1. So this is going to be sort of our baseline, where maybe if both numbers are bigger than the min cost by 2, that this would be a better way to swap, a more optimal way to swap, right? And so now what's left to do is just basically doing the swap with the smallest with the largest each time. But then at the same time, comparing that min. So let's say each time we'll take A1, the min of A1, B1, but we'll take that with the min cost, right? And we'll do the same, sorry, here is Bn because we are doing the smallest with the biggest. And next step, we'll do min A2 with Bn and min cost. And same thing, n minus 1 here, A3 with Bn minus 2 and min cost. And that's the idea. Now, one additional thing I want to mention is that instead of having 2 here, we can just decide to put them in the same array, right? Where the first is the smallest value, the second is the highest value, and just pick from the smallest associated with the biggest, and pick from this one associated with this one, right? So that's just a different way of implementing it that we will do in our implementation that I want to mention. Yeah, so that's, I think, a good overview here. I don't want to make the video too long, but this is a good overview of the solution. Now let's jump in and code it up. Okay, so implementing this now, what we said first is we need a counter for each of the baskets. So for the first basket, we are going to use a counter that is basket 1. Then for the second basket, it's going to be for basket 2. And then after that, we want an overall count, right, for both. And we are going to do our first observation first. So we get the number, the count, and we are going to do this on the count.items. Now, the first observation, we said if the count is odd, that means it's not possible to make them equal because there is a value that is in one of the baskets that has no corresponding value in the other basket, right? So that's the first thing. The other thing I want to do here is make this sorted, just because of the thing we mentioned in the overview that we want to pair the smallest with the biggest, right? And so here, what we are going to do is we are going to create a new array, and we are going to keep only the leftover in this array. And by leftover, I mean if you have 3 threes, let's say in basket 1, let's say 2 threes and 2 twos and 1 3 or something like that, And then you have in B2, you have maybe 2 2s and a 1 and maybe 3 1 or something like this, right? These already match, right? So no need in keeping them, right? So no need to keep them around. So that's what we are going to do here. So the frequency of what's left is that basically we take the count for this number, let's say occurrence here, to not interfere with this count. So the occurrence divided by 2, this is basically what we have matching, right? That we want to remove from the frequency minus the minimum of the count 1. Okay, let me explain this, why we have this. So this min, right, is what's already, will give you what's already equal between the two baskets, right? And what's remaining is only what we need swapped, right? Because you might have 2 2s, right? Like this. Okay, and in basket 1, and let's say in basket 2 you have just 2 2s, right? So we want to get rid of these, right, and just leave these 2 2s because there is no matching ones here, and we want to maybe potentially swap one of them with, let's say, 1 and have them match, right? And so we want to remove the excess that we know already matches, right? And you may say, why we do divide by 2 here? Well, we do this because each swap, right? Each swap uses 2 values, right? Uses 2 occurrences, right? Okay, so I hope that makes sense. And now we are going to add to the array numbers for each frequency. Okay, and so if we do this, what's going to be left is only the leftover that's not matching already. And now we can just do our final result that will return, which is the total cost, and we'll return result. The first thing we want to do is what I said about using the min value to do the swap is sometimes going to be better. And so that's just going to be the min of all the remaining value of all the values, right? So the count keys multiplied by 2, because we can use that number as the value to swap 2 times instead of just swapping the values. And now we are going to go with just the now since these values are sorted, this array is sorted. If you are not sure, you could also do just array.sort. Right, but it's not needed because we went through this in sorted order. Okay, and so now we only need to go through the length of the array up to the first half of the array, because that's the smallest side, right? So we have the array here that has all the values, right? Okay, and we want to associate the smallest with the biggest, but each time the smallest is going to be the min. That means basically the cost is going to be just the values of the first half of the array, because that's the smallest, right? So instead of like going through it and every time picking the smallest and biggest and realizing the first value was the smallest and then comparing this one and this one, realizing this one is the smallest, what will end up happening is just we will get the first half of the array. And so that's exactly what we want to do here. And so res is going to be just the sum, just adding up the min of the min cost and the value here, right? Because this will be the smallest value between the smallest and largest anyway. Okay, and so now let's run this. Yeah, this needs to be occurrence. Okay, looks good there. Let's submit. Looks good as well. Yeah. Yeah, so I think that's pretty much it for this problem. Now, in terms of time complexity, this is, if we take n as the sum of the length of the two baskets, this is O over log n. Or if we want to take the more sophisticated, like just the length of 2, n1 plus n2. This is going to be also up to of n plus 1 plus n2, because that's the max of what the array can be. And then we are using this here, which is also of n1 plus n2 space, and same thing here for c1, c2 overall. So this is overall space, and this here is of n1 plus n2 time, and so overall it's of n1 n2 plus n2, or log n1 plus n2 time, and this is of n1 plus n2 space. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.